I'll be covering 7 sections. Let's get right into it. So what is a limit? I'll be graphing a parabola here just to show what happens with a limit. So let's see what happens as x approaches -2. And as you can see, the function value is decreasing until we get to equals 17. And we can algebraically solve this and plug -2 into the function and get 17. I'll show you a classic limit trick here. Let's graph the function, and as z approaches 8, as you can see, we see that it approaches 16. But when you evaluate the function there, you get undefined. And if you algebraically solve this by plugging in z is equal to 8, we get 0 over 0, which is called indeterminate form. So to solve this, we have to factor the numerator, cancel out the z minus 8, and you get 16 at the very end. This shows that the limit means approaching the value is not the same as evaluating the function. We have a piecewise function here, which means graphing two different functions. And now this limit says approach 1 from the right side, and we get 2. Now this limit says approach 1 from the left side, and we get -2. But if we come from both sides, we get 2 is not equal to -2, which means the limit does not exist. And if you evaluate the function, you get -2. Here's another important example. Absolute value functions are just piecewise functions, so that means you can break them into cases. For x greater or equal to 2, we get 1, and for x less than 2, we simply get -1 at the end. So let's track the answer to the top right of the screen and graph this. And as you can see, when we do graph this, we get that the left-sided limit does not equal to the right-sided limit. The limit does not exist. We need to solve some questions graphically. Here's an example. Let's find the horizontal asymptote. As x approaches infinity, you see it goes to 0. And as x approaches negative infinity, we get it goes to 0, but from the negative side. So we have a horizontal asymptote. For vertical asymptote, we ask, where does the function break? And that's when the denominator is equal to 0. And we can factor that until we get x is plus minus 2. So let's put the dashed lines there, and let's graph the function here. And after you graph the function, we see this. X can now go to infinity from the right side. So there's 3 different types of discontinuity. And in the first problem, you can see that the limit on the left side is 1.5 and the right is also 1.5. So this means the limit exists, but the function does not equal to the limit. We call this a removable discontinuity. In our second problem, we don't have a point in the function, and the limit is also equal to each other. So this means we have a removable discontinuity again. And in the third problem, the function jumps. So you can see the left function and the right functions do not agree. This means it's a jump discontinuity. And lastly, we have two functions going to infinity, but on opposite ends, but you only need one. And this is called the infinite discontinuity, or unbounded behavior. I'm going to explain the intermediate value theorem, and you can read this if you want. So let's graph a cubic function, and we're only interested in the interval of -1 to 1. That's our AB, and the function values are shown there. And even if we change our function, as long as it's continuous, it must cross the x-axis or any point we choose that's in between. That point must exist. So here at point C, we have f of c is equal to 0. Here's an example of the squeeze theorem. We take this function, we take sine because it's always between -1 and 1, and times everything by x squared. Now, if we graph this, you can see that negative x squared is the lower bound, and x squared is the upper bound. And our complicated function must be in between. So what we can do with this information is we take the limit of the lower bounded function and take the limit of the upper bounded function, and they're both 0. So the overall answer is 0.